Probability is a topic that we're going to be studying for quite a while. The problems can be relatively simple or relatively complex. In this video, we're just going to look at sort of the basics of probability to get us started. The main thing I want you to remember about probability questions, whether they're simple ones or complicated ones, is that probability equals successes divided by outcomes. We're going to be able to express that as a fraction, as a decimal, or as a percent. But the main thing in every probability question is we're looking for how many successes are there, how many outcomes there are, and we divide that. Let's talk about that word successes. A success has nothing to do with winning or losing. Instead, a success happens when we meet the condition that we're looking for. We'll look at an example to really sort of make sure you understand this word success, because it's very important as we're calculating probabilities. A single fair coin is to be flipped. What is the probability of getting heads? Now, I mentioned that it's a single fair coin in this example. For all of our work in probability, we're going to work under the assumption that the coins, the cards, the dice are all fair. There's no weight in a dice to make it land a certain way that would throw things off. We're not going to bring those sort of situations into play. We're going to work with fair materials. Now, thinking about a fair coin that is going to be flipped, and we want to know what is the probability of getting heads. This is a very simple example, but it's a great one for us to start out with. Remember, probability is equal to successes divided by outcomes. So those are the two things we need to find here. Well, how many outcomes are there when I flip a coin? Well, there's heads and there's tails. That's it. So there are two possible outcomes. That's going to be our denominator. And now, what are our successes? Remember, successes don't have anything to do with winning and losing. I don't win anything here if it's heads. I don't lose anything if it's tails. But the question said, what is the probability of getting heads? So heads represents my successes. It's what I'm looking for. How many heads are there on this coin? Well, there's one. So I have one success and I have two outcomes. So the probability of getting heads is 1 out of 2, or 1/2. That's this probability written as a fraction. I also mentioned that we could write this as a decimal. If we want to convert this to a decimal, we just divide 1 divided by 2, and we get 0.5. And if we wanted to write that as a percent, let's see, converting a decimal to a percent, I need to move the decimal point 2 places over, so that would drop a 0 here, and so this would be 50%. All of those are a way to express this probability. As a fraction, it's 1/2. As a decimal, it's 0.5, and as a percent, it is 50%. Let's look at some more. A single die is rolled. What is the probability of getting a 4? Let's think about the outcomes that we have, because remember, probability is equal to successes over outcomes. So what I need to know is, how many outcomes do I have? What are my successes? Well, on a single die, the outcomes would be 1, 2, 3, 4, 5, and 6. So I have 6 outcomes. So here I have 6 outcomes. What is the probability of getting a 4? Well, let's see. How many sides does the dice have a 4 on them? Just one? So I have 1 success and 6 outcomes. So the probability of getting a 4 is 1/6. With this same single die that's rolled, what is the probability of getting an even number? Let's see. I still have those same 6 outcomes. Now I have to decide, what are my even numbers? Well, if it helps you to list them out, you can go ahead and do that. All of the outcomes are 1, 2, 3, 4, 5, and 6. And now we can decide which ones of these are even numbers. 1 is not, 2 is even, 4 is even, 6 is even. So I have 3 successes in my 6 outcomes. So the probability of getting an even number is 3 out of 6, or 3/6. which you could reduce to 1/2. Sticking with that same single die, let's look at two more questions. What is the probability of getting a 10? Well, again, probability of successes over outcomes. I know I have 6 outcomes, and how many of those would be successes? How many of the sides of a single die would be a 10? Well, I have 1, 2, 3, 4, 5, and 6. None of them are a 10, so I don't have any successes. So that probability is 0 out of 6, which also we could just say is 0. That can't happen. What is the probability of getting a number less than 8? Well, I still have 6 outcomes. How many successes do I have? How many numbers on that single die are less than 8? Well, all of them are. So all 6 of them are successes. So the probability of getting a number less than 8 is 6 out of 6. That probability is just 1. And this brings us to an extremely important idea. And that idea is that all probabilities are between 0 and 1. Something that absolutely cannot happen, like getting a 10 when we roll a single individual die, that probability is 0. Something that absolutely cannot happen has a probability of 0. And something that absolutely must happen, like getting a number less than 8 when we roll a single individual die, that probability is 1. So if it can't happen, the probability is 0. If it must happen, the probability is 1. So all of our probabilities are between 0 and 1. This is a really important idea, and it can help you when you're solving these problems. If you come up with an answer of 1.73, you know you've got it wrong, because all probabilities have to be between 0 and 1. Keep that in mind. Let's look at some more. A really common situation for us will be 2 dice are rolled and the sum of the faces is found. In your book, you'll see a table of all 36 possible outcomes. Wait a second. What? 36 possible outcomes? What the heck? How can that be? If I roll 2 dice and take the sum, I get these possible outcomes. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. Anybody who's played Monopoly knows that these are the only outcomes when you roll 2 dice and take the sum. How come you're saying there's 36 possible outcomes? Well, wait a second. We're all familiar with the fundamental principle of counting. How many possibilities are there on the first dice? There are 6 possibles on the first dice. And how many possibilities are there on the second dice? Well, there are 6 possibilities on the second dice. And what do we do with those? We find a number of possibilities for each and multiply them together. So that means there should be 36 total outcomes. Well, I'm still not seeing 36 possible outcomes up there. I'm seeing 2 through 12. Well, hang on just a minute. There's more than one way to roll those numbers. For example, rolling a 3, you could get a 2 on one dice and a 1 on the other, or you could get a 1 on the first dice and a 2 on the other. So if there's more than one way to roll each of these individual outcomes, maybe there really are 36 possibilities. Let's look into this a little further. We just mentioned rolling a 3 and said that there's more than one way that that could happen. And let's pretend we've got an orange colored dice and a green colored dice. And I could get a 1 on the orange dice and a 2 on the green dice. That's one way I could roll a 3. I could also roll a 3 with a 1 on the green colored dice and a 2 on the orange colored dice. And those are different outcomes. You can see the numbers on the dice have changed. The green dice used to have a 2, now it has a 1. The orange dice used to have a 1, now it has a 2. So these are 2 different ways that I could roll a 3. This is going to be true for the outcomes when I roll 2 dice and take the sum, and that's what you'll see in the table in your book. Let's take a look at rolling a different number. When rolling a 4, there are 3 different ways that this could happen. I could get a 1 on the orange dice with a 3 on the green, a 2 on the orange with a 2 on the green, or a 3 on the orange and a 1 on the green. This usually raises questions for students. what happens is they say, well, wait a minute, you've counted a 1 and 3 twice. Why didn't you count 2 and 2 twice? Well, I want you to take a look at the colors carefully. If you take a look at the colors of these two rolls, you can see that the dice have actually changed. In the top one, a 1 with a 3, it was the orange dice that had a 1 and the green dice that had a 3. In the bottom one, the orange dice has a 3 and the green dice has a 1. That means that those two outcomes are different from each other, and so we need to count them as being different outcomes. When we look at the 2 on the orange and the 2 on the green, if I were to try to change those, I'm still going to have a 2 on the orange and a 2 on the green. The result's going to be the same. This isn't about what position they're on the table. This is about what is showing on the dice. And since there's no two different outcomes with a 2 and a 2, we only count that once. We count the 1 on the orange with a 3 on the green as different from the 3 on the orange with a 1 on the green. Those are two different outcomes. But a 2 with a 2 is only one outcome, so we only count that once. If you struggle with this at all, try to find two different colored dice in your house and give this a shot. You'll notice to go from 1, 3 to 3, 1, you actually have to change what's showing on the dice. But with the 2 and the 2, you don't have to change the dice. And that's why that's one outcome as opposed to the 1, 3, and 3, 1, which is two different outcomes. Now let's look at a probability question involving this situation. When rolling two dice and finding the sum, what's the probability of getting a 4? Well, remember way back there, probability is successes over outcomes. And in this case, we have 36 outcomes. And how many of those give us a 4? How many successes do we have? Well, we can see that in the chart over there on the left. I have 3 ways that I can roll a 4. So I have 3 successes and 36 outcomes. So the probability of rolling a 4 is 3 out of 36. You could reduce that to 1/12. And if you wanted to write this as a decimal, rounded to the nearest hundredth, you could divide 3 divided by 36 and get 0.08. And if you wanted to write that as a percent, we could move the decimal point over, and this would be 8%. We have one more situation that's great for studying probability. It's working with a deck of cards, and I'd like to go ahead and do that next. Most of you are probably familiar with a standard deck of cards, but just in case, let's go ahead and talk through that. In a standard deck of cards, there are 4 suits. There are spades, which are black, clubs, which are black, hearts, which are red, and diamonds, which are red. Each of these suits consists of 13 cards: an ace, a 2, 3, 4, 5, 6, 7, 8, 9, 10, a jack, a queen, and a king. These 3 are often referred to as face cards because they have pictures of people on them: the jack, the queen, and the king. So those 3 are called face cards, and there are 13 cards in each suit. If we have 4 suits, each consisting of 13 cards, that gives us a total of 52 cards in our deck. So a standard deck of cards is made up of 52 cards, 13 spades, 13 clubs, 13 hearts, and 13 diamonds. Now let's look at some probability questions involving a deck of cards. One card is drawn from a standard deck. What is the probability of drawing a queen? Well, remember, probability is always successes over outcomes. So what we need to do is figure out how many outcomes we have, figure out how many successes we have, and then write that down. So let's see, we know in our deck we have 52 cards, so there are 52 outcomes. How many queens are there? Well, there's the queen of spades, queen of clubs, queen of hearts, queen of diamonds. So I have 4 queens in the deck, so the probability of drawing a queen is 4 out of 52. What is the probability of drawing a club? Well, here again, I still have those 52 outcomes. And how many clubs do I have in my deck? Those would be my successes. Well, I have 13 clubs in my deck, so the probability of drawing a club is 13 out of 52. Let's look at a couple more. These two questions look really similar, but they're very different. What is the probability of drawing a king or a diamond? What is the probability of drawing a king and a diamond? Now remember, we're only drawing one card. The words and or were really important to us back when we did set theory, and the same thing is going to hold true here. If we're looking at or, we have to meet at least one of those conditions, and we're going to join them together. When we're looking at and, we have to meet both of those conditions. So keeping that in mind, the probability of a king or a diamond. Well, I know I'm going to have 52 outcomes, and the hard part of this is figuring out my successes. What are my successes? Well, let's see. I've got 13 diamonds, and I have 4 kings. So I just add those together and have 17 success. Wait a minute. What have I done here? I've counted 13 diamonds and I've counted 4 kings. I've counted the king of diamonds twice. So instead of looking at this way, maybe what I need to do instead is I'm going to count the 13 diamonds, which means I've counted the king. And then I'm going to count the 3 other kings, which means I've got 13 plus 3. I join those together. This is or. So I join those together, and I have 16 successes and 52 outcomes. So the probability of getting a king or a diamond is 16 out of 52. Now let's look at the probability of getting a king and a diamond. This is and. So in order to have a success, I need to meet both of those conditions. Well, I know I've got 52 outcomes. I can go ahead and do that part. Now the question is, how many successes do I have? How many cards in my deck meet the condition of being a king and meet the condition of being a diamond? Well, there's only one of those, the king of diamonds. That's the only card in the deck that'll do that. That's a king and it's also a diamond. There's only one of those. So the probability of getting a king and a diamond is 1 out of 52. Some probability questions will be relatively simple. Some can get more complicated. When you're doing probability, just remember, we're looking for successes over outcomes.